Part 3 of Lecture 8. So this is actually the most important part among these two lectures. We're going to talk about convolutional neural network. And let's first summarize what happened so far, starting from Lecture 7. So we want to find some kind of feature for images so that they can be used in training a machine learning algorithm. So we started with, say, using the gradient of the image, and somehow we can combine them to figure out which pixels are edge pixels, which pixels are corner pixels. And it turns out this cannot be used as features to directly train a neural network. So we move on to get some kind of more complicated feature, something like SIFT, which has some kind of good computer vision properties, like we are okay with translation, rotation, and scaling. And it turns out this is kind of too complicated. It is too time-consuming to compute this for each image. So no. And then the next thing we did is something simpler but still works, the Hawk features, and they actually work. So for example, they can be combined with support vector machines to classify whether the image is a face or not. So now it's kind of working. And at the end, we did, in the previous part, we did Viola drones, which they are even simpler features. But each individual one does not work. But if you combine many of them, they actually work well, and they're really fast. So it's combined with decision trees. And the problem is they are specific for something like face detection in an image. So it's not that general for any kind of computer vision task as well. So far, there is a big problem with this. So what we are trying to do is we're given an image, we have those pixel intensity as the original features, and what we're going to do is we are going to use some special features, special filters that we think they are meaningful to create some features that we want, and then we use these features that we created by hand, basically, to predict why we can train them using SVM and or neural network or stuff. So usually this is called feature engineering. So we are creating features ourselves, basically. So we do this by using some kind of domain knowledge, or in computer vision, we often choose the features by just experimenting with different kind of parameters and figure out the best one. So they may not be that great, and it needs a lot of engineering. So what if we just do this? We still use the image pixel intensities as the features, but we're going to train the filters. So we're going to just treat these filters as regular weights. It's like a matrix of weights, right? And we just train them inside a neural network, and then it can directly output the label. So that would be great. And that actually is great, and it's called convolutional neural network. So again, the main idea is just we are treating these filters as weights that we train. And remember, convolution is just like some kind of special dot product. So we're going to use the same idea as the regular neural network, and instead of having dot products, we're just using convolutions. So the idea of the algorithm is very simple. We filter an image, and then we pull. We'll talk about what pulling is later. And then we basically feed the result to a neural network, or we can feed the result back to another filter and then get another output, and then feed the result to a neural network. And when we train them, we still use backpropagation and include these filters as a part of the set of weights, basically. So let's talk about some special properties with convolutional layers. So the regular hidden layers in the neural network that we talked about in lectures 3 and 4, they are called fully connected layers. And the idea is basically the next layer unit is just the activation function, so the nonlinear function applied on this linear combination, or just the dot product between W and X. So here, as I said, we're just going to replace this dot product by convolution. And actually, that's the only difference. We're still doing a nonlinear activation. And another thing, yes, so here, these A's are individual independent units, so they are like a vector of units. But here, the activation would be a matrix. So that's, I guess, another difference. And of course, we're going to give it like different names. So the output or the activation of the convolutional layer is usually called the feature map. It is also called the activation map. I actually like the word activation map more because it's like in a regular neural network. So they are basically a matrix of activations, as I said. And here we can have multiple feature maps or multiple activation maps in the same layer. So it's like multiple hidden units. Here is multiple matrices in the same layer. And as I talked about before, the output of the convolutional layer can be either the input of another convolutional layer or can be flattened into a vector to be the input to a fully connected layer. So what I mean by flatten is if you have a two-dimensional matrix, you can just take the first row, second row, third row, and just align them into a long vector and treat these as individual independent units and put these as the input of a fully connected, or at the end, softmax layer. So let's use a diagram to draw what a two-dimensional convolutional layer look like. So note that we're going to use the same set of same set of filter weights to convolve to get all the regions, to get activation for all regions. So we're not going to use different filters for different regions. So here, W1, W2, W3, W4, suppose we have a 2x2 filter, then we're not going to have a 2x2 filter here and another 2x2 filter here. It's going to be way too many weights to train, so we're not going to do that. And also, we want this to be like location invariant or translation invariant, so we may also want to use the same filter to apply on all different regions. We can use different filters in parallel, but here let's just do one first. So we convolve this with this filter to generate one number. So remember, the convolution between these two produce only one number, and then we just move this window to the right by 1 pixel, so it's stride 1, and then it generates the second one, say 1, 2, and then move it to the right by 1 pixel again, generates 1, 3, and so on. So as I promised, we can use another filter in parallel, say W prime, and we filter the same regions, so the first one and second one, to generate another parallel activation map. So we are not using this filter on this resulting activation map. We're basically doing these two things, using these two filters in the same layer. So we can do more than two, but the problem now is if we continue to do this, it's going to be like a tree. So there will be exponential number of activation maps where we're not going to be able to deal with that. So somehow we need to combine these back into like one activation map in the next layer. So we can add them up, but we're not going to do it. We're going to do something more complicated. Basically, we're going to treat these, we're going to combine these into a three-dimensional array and use a three-dimensional filter. And let's talk about it here. So what we're going to do is we're going to treat it as kind of a block. So the way you might want to visualize it is this is the activation map corresponding to the first filter in the previous layer, and this is the second one, and they are put in parallel into a three-dimensional array. And our filter will be three-dimensional as well. So for example, we can have a filter that's 2 by 2 by 2. Then we have 8 weights, 1, 2, 3, 4, 5, 6, 7, maybe let's not write 7, and 8 here. And what we're going to do is we're going to filter basically the same way as the two-dimensional one. We're going to multiply this 3D cube. So these 8 pixels basically with this filter, and not actually multiplying. It's called convolution, and we are going to basically treat this as a region, and then we convolve with our filter. And remember, we only get one number here. Okay, and then we're going to move this around, maybe move this to the next pixel, move this to the right by 1 pixel, and convolve with the same filter and get another single number. So that's basically what we are doing for a three-dimensional filter. And remember, at the beginning, I talked about mathematical images. So if we have mathematical images, they are 3D at the beginning. So they have voxels instead of pixels. So each pixel, a voxel is like a three-dimensional thing with a single intensity. So at the beginning, in the first layer, we will have a three-dimensional filter. Well, this drawing may not be nice, so let me actually load one that's drawn by someone else. So basically something like this. So you have a 3 by 3 by 3 filter, and it's combined with this 3 by 3 by 3 region to produce one unit. And you can just move this around to get many activation maps. So that's the three-dimensional convolution idea. And now let's move on to the pooling layers. So the pooling layer, the idea is basically we have maybe the image is too large, so we have too many pixels, so we want to size down basically. So what we can do is actually a very simple thing. We can just combine these, say 2 by 2, 4 pixels into one value. So usually it's called downsample or subsample. So we just either take the max in this region or take the average of the values in this region and make it into 1. So that would be our first one. And then usually the pooling layers, they are non-overlapping. So each region will be like this, not like move to the right by 1 pixel or something. So this will produce activation number 2, and this will be 3. So it's basically a simple downsampling, and we're using some kind of fancy name. But in any case, we have 6 by 6 images in the previous layer, and now it becomes 3 by 3. So we basically have less units to deal with. And here it's either max or just taking the average. We don't need a diagram for pooling. I already have it. So the next thing I want to talk about is how to train them. So I think the mathematics is kind of very complicated, so I don't want to actually show you why these work. So I will put the formulas here. I posted a link to the detailed mathematics why this works. If you are interested in the mathematics, you can take a look. You will not be asked to implement these from scratch. So if you want to actually implement these, you should use a package. So I'm not asking you to learn the mathematics behind this, but actually it turns out it's actually very simple. So the gradient of the cost with respect to these weights, these are the filter weights, it's just the input unit convolved with the next layer gradient. So we have a convolution. So again, if you need to look at the mathematics to see why this is the case, and we're not going to talk about it here. And similarly, if you want to find the gradient with respect to the input units, you need to rotate the filter by 180 degrees and then convolve it with the next layer gradient. So again, I will not worry about the specifics. Okay, so in the pooling layer, the gradient is actually very simple. You can just differentiate those two functions yourself. The derivative of the max is just the max unit is 1, otherwise it's 0. And the average, you can directly take the derivative, it's just 1 over the number of units. Okay, so next I want to talk about some specific and very famous convolutional neural networks. The first one is called AlexNet, and it's used to recognize handwritten digits. So let me first show you a diagram of the architecture. Let's find it. Where is it? AlexNet. Here. So you have an input image. You're going to use a filter here. I remember it's a 5x5 filter. And then you would convolve each region with this filter and get the activation here. And you have 6 of these filters, so there are 6 different filters. So you get 6 times this number of weights in the filters to train. And sometimes you have the bias term, sometimes no. But here for AlexNet, I remember there are bias terms, so you have other bias to train. But in any case, the next step is, they are calling it subsampling. We are calling it pooling. So they are the same thing. I remember it's average pooling. So it's just combining a 2 by 2 region, take the average and make it 1. So it reduced the image size from 28 by 28 to 14 by 14. Okay, and the next layer, it's actually a 3-dimensional filter, and it combines multiple of these activation maps into one. And then there are multiple of these 3-dimensional filters to create the first one, the second one, and third one. There are actually 16 of them. Because the images are smaller, so we can have more activation maps in the same layer. So we're going to create 16 of them, and then we do downsampling again, so a 2 by 2 pooling layer again. And then we get to this stage. So at this stage, we're just going to treat them as independent unit instead of arranging them in an array. So we're just going to flatten these very small images into a very, very long vector. And then this vector is fully connected with the next layer units. These units are basically 128 independent hidden units. And basically every unit here is connected to every unit here. So there are lots and lots of weights in this region. Not really many weights here because they basically share the same filter. So here they have lots and lots of weights, and here there are lots of weights in between these fully connected. And in the last layer, it's just the softmax layer. They're calling it Gaussian connections. We're just calling them softmax. So this is basically the structure. And let's actually look at some examples, basically what they can do. So this is the official website of LeNet 5. And let's look at something that it can do. So the first one is what we want in computer vision is translation invariant. But basically, is if the 4 appears at different locations, it still works. And scale, so if you scale 4 up and down, the classifier still works, the neural network still works. And also rotation, so it doesn't matter what the orientation is, it can classify the 4 correctly. And it only works for small rotations, so plus or minus 40 degrees, because I say if you flip the 4, it's like not a 4, so it's expected. And squeezing as well, so squeezing like this, and stroke width, so it can be very thick. So these are basically good properties that we wanted in computer vision with something like SIF features. So good. And also it's resistant to noise. So if we have noise, it still works. And similarly, other types of noise still work. So it's basically like what the Gaussian filter is doing. So basically it can replicate the things that a engineered features can do. So basically the idea is when training on lots and lots of examples, those filters in the previous layers can actually somehow replicate those features, the filters that we engineered by hand, so they can do all of those things that, say, Sift and Hug can do. And here there are some kind of unusual styles, like 2 written like this, 3, and some strange 4, 5 with part missing, and so on. And also there are some thing called weirdos, like 2 written with a bunch of circles, and 3 that's it's not really a 3, and 4. And all of these things are actually classified correctly by the network, so it's kind of amazing. This, well, looks like a 4, 5, 6, and 8 is just two circles. Okay, so that's what I want to talk about here. And there is actually a very nice visualization. You can actually draw something here, and you will classify as 3, which is right. So let's look at the network structure again with this very nice visualization. So if you look at each pixel in the first activation map, in the first layer activation map, there are 6 of these. If you look at each pixel, they are using the same filter on different regions of the input image. So in this activation map, basically we have the same weights, and we just apply them on different regions of the original image. And here we have different set of weights to produce another activation map. And then in the next layer, we're having the pooling layer, so we just combine like 4 pixels into 1, so we just get a smaller image that looks like the same. And in the next layer, we have a 3-dimensional filter. So basically here, according to the visualization, we're combining these 4 activation maps into 1. So I can't really count. I think it's a 5 by 5 by 4 3-dimensional filter. So it combines like these 5 by 5 by 4 units into 1 unit in the next layer. And we have like 12 of these. So each one is connected to, I think, either 4 or 3 of the previous layer activation maps. And then we have another pooling layer combining 4 units into one. And then here we're treating like all of those pixels in these small images as like independent pixels. So in the next layer is fully connected. So every unit in the next layer is connected to all the pixels in all these small activation maps in the previous layer. So starting from here, it's fully connected, and they have all different weights. So if you look at these, they have different weights, and they are all connected. And in the next layer is the same. Every unit is connected to all units in the previous layer, and like this. And the last layer is just a softmax layer. Okay, so that's what I want to show you. And let's get back here, and let's talk about another network structure called AlexNet. Let's find the image. Where is AlexNet? Here. Okay. So if you look at these, they are actually similar. So at the beginning, we have a 11 by 11 filter with a stride of 4. So it's moving around every 4 pixels. And then it constructs a 3-dimensional. Basically, it constructs multiple activation maps. Here, I think there are 48 different activation maps. And then they have these kind of 3-dimensional filters now to basically somehow combine multiple activation maps into one. And then we have like a bunch of them, like 128 of them, and so on. So in the next layer, we still have so here we have max pooling, and then these images will be smaller, but then we convolve again with some kind of filter. And this is basically done many times. And then at the end, we have these, what they call dense layers, called AlexNet. And next, there are even larger neural networks. And let's look at some example as well. So VGG, I don't actually know what it stands for. So if you look at the structure, it's actually similar. So here, it's the input image is already 3-dimensional because it's using color image instead of like black and white or grayscale images. So it's the input is already 3-dimensional with R, G, and B. And then we have 3-dimensional filters in between, and we have these pooling layers in between to make it smaller. And at the end, we have fully connected layer, and we have the softmax. So basically similar idea, just with different parameters and deeper. Next. We actually talked about this before, I remember. It's the Google net, or people also call it Inception net because it's very deep. And there are these special Inception modules. So these things are called Inception modules. So basically, it's instead of going very deep, which will cause problems, it goes a bit wider, so it applies different shaped filters in the same level, basically. So here, for example, I think it's something like 3 by 3, 5 by 5, 7 by 7. So there are basically different size filters in the same level, and at the end, they somehow combine them back into one single activation map. So that's the Inception module, and they are used again to avoid training very, very deep neural networks. So the problem with very deep neural network is that there will be something called the vanishing gradient problem. So vanishing gradient. So when we talk about natural language processing, like in the next lecture, we will see this thing again because we are effectively training infinite layered neural network. So when we do backpropagation, when we go through too many layers, the gradients will be close to zero. Basically, everything will be zero. So the training will stop. So that will be a problem. And again, we will talk more about this later. And the Inception net or the Google net basically provides a method to deal with this problem. And it also solves the problem of overfitting, I think. And at the end, there's the RASNet. Where is the RASNet? This. Oh, it's getting kind of slow. Sorry. Okay, so which one is the RASNet? So this one is VGG19. So these two are actually the same thing. And this is just the basic 34-layer neural network. So that one is the RASNet. It stands for residual net, and I think the residual net that they actually trained is like 152 layers or 154 layers, so it's a lot deeper than this. So again, with very deep neural networks, there will be the problem that the gradient will become zero when training a very deep neural network. So there needs to be methods to fix it. And with ResNet, they have these kind of skip layer connections. So you can skip a layer, basically. You can connect the previous layer to directly skipping 2 layers to the next layer. So I will not spend more time talking about these details. I already posted the link to these original papers. So if you want to look at the mathematics, for example, you can look at them. You can also look at their explanation why they structure the network like this. So they are very interesting papers, and of course they're kind of difficult to understand. So, but if you are interested, I posted these papers already, and they like explain why they're doing this. Okay, so I'll stop here.